Hello, ladies and gentlemen, and welcome back. We're on question number 24, our second last question on our 2012 Fermat paper. In equilateral triangle PQR, S is the midpoint of PR, and T lies on PQ so that PT is 1, TQ is 3. So overall, the side is 4, 4 down here, and if S is the midpoint, we get 2 and a 2, and well, it's an equilateral triangle, so I get a 60 degree here. I think we got a 30, 60, 90 triangle with P, S, and T. Okay, anyway, that's just initial thoughts here. Now, many circles can be drawn inside quadrilateral QRST so that no part extends outside QRST. Yeah, I would argue that's what it means to draw something inside. That, okay, I can have a circle here, circle here, circle here. Something like this is too big because it sticks out. And what do they want here? The radius of the largest such circle. Okay, the largest such circle. And so if we sort of imagine starting a point and sort of inflating a circle or a balloon almost, a circular balloon, eventually you'll hit a side. And if you keep making it bigger, you'll go outside the side. But if we shift the start a little bit more, you might be able to fit more in. And it's entirely possible. The biggest circle would be one that's pressing on sort of all sides of this quadrilateral. And so we might get something that's tangent to all four sides, and then we could work out the radius there. The biggest thing would have to be something that's tangent to all four, but that's not necessarily possible. So let me briefly explain that. If not all quadrilaterals, like any triangle you make, you can always have a circle that touches each of the sides. This is called the in circle. Circles always have triangles always have an in circle, but not every other shape does. Quadrilaterals, some of them do. Some quadrilaterals, like a square, you can get a circle that touches all the sides exactly once. But if you imagine something like a really, really long trapezoid, then yeah, I can get a circle over here that touches 3 sides, but there's no way it's going to reach this side and still stay inside the quadrilateral. So that's a possibility that we might have to deal with. Anyway, let's draw this thing and see what we can see. So as I remarked, this is a equilateral triangle. Yeah, it's a little more believable. And we've got 2 here, 2 here. Side length of the whole thing is 4. We have 1 and 3. And we have 60 degrees here. Now, one thing you can do, you could use the cosine law on this triangle up here, PST, and you can work out the opposite side. But knowing 2 sides and the common angle between them, using the cosine law definitely gets you the other side. So it's kind of guaranteed. And so if you know a more common triangle that has a 2, a 1, and a 60 degrees, with the root 3 on the other side, this is the 30, 60, 90 triangle, very special, very useful triangle, comes up a lot. If you already know that, you can just jump straight to this is a root 3 here. You don't have to do the cosine law. And then if you got 1, 2, root 3, and you got the 60 there, well, you know the other angles here. And we do have other angles here inside our triangle, 260 degrees. This will have to be a 90 degrees, and this will have to be a 150. And with all the sides, the 2, the root 3, the 4, and all the angles here, I know everything really that there is to know about this quadrilateral. So we've got all the information we need. It didn't take that long to figure out. Now we have to start worrying about circles. Okay? Now, just because you can't always get an in circle, you should be able to always get a circle that can touch 3 sides in common. So, well, first let's see, can I actually get something that would touch all 4 sides? Now, if I do have a circle here that touches all 4 sides, what would I have? I'm going to draw the circle first. There's my circle. What does a quadrilateral look like if your circle touches all 4 sides? Something like that. Okay. Now, one of the nice things about tangent lines and circles, if you have 2 tangent lines that meet at a point, the distance from that point of intersection to the tangent points on the different lines is equal. Okay, these two here are equal. So we can use that to realize, those two are equal, these two lengths are equal, these two lengths here are equal, we'll use the red again, these two lengths are equal. Now, what does this tell me about a quadrilateral that has an incircle, a circle that touches all four sides, is tangent to all four sides? Well, if you were to call, the yellow one A, and then we have B, C, and D, look at these two opposite sides. What's the sum of those two sides? Well, A plus B and C plus D. What's the sum of these two sides? So they still have a yellow, a blue, a red, and a green. It's still going to be an A, a B, a C, and a D. So if I have an incircle, I can confidently say, thanks to my circle properties, that opposite sides must add up to the same amount. Now let's go back and look at this quadrilateral. If there were an incircle, if there was something that did manage to touch all four sides, you'd need 2 plus 3 to be the same as 4 plus root 3. 2 and 3 add up to 5, so we would need a 1 up here, not a root 3. So, unfortunately, we're not so lucky as to get an incircle. No incircle. Okay. So, question's a little harder. That's okay. It's 24 on the Fermat paper. We should be prepared for something. Okay. So we can't get all four sides, but you should be able to get 3 sides. Now, if I know my side lengths, which I do, I know side lengths, I know angles, can we talk about radii? Okay. That's 3 sides. Let's add these radii. Radii from the center always hit the points of tangency at perpendicular or right angles. Okay. And what can we say here? So if got an R here, this is my radius. Well, we can still make the observation that the points of intersection to the points of tangency will be the same lengths. And so what can we do? Well, if we connect up the points of tangency to the centers, what we get are pairs of equilateral triangles. Or not equilateral triangles, pairs of congruent triangles. Okay? And if we know the angles here, maybe call this angle alpha and this angle down here beta, if they're congruent triangles, then we have to have the same angles inside here. So these angles up here will both be alpha over 2. These ones will be beta over 2. And then if I just tilt the picture a little bit, got this R here, alpha over 2, beta over 2. Well, if that's alpha over 2, this is going to be 90 minus alpha over 2, and this would be 90 minus beta over 2. We should be able to work those to get A and B, these lengths here, and then they would sum up to a side that we know. So we can use a little bit of trigonometry. For example, we could use something like the sine law to say that A is R over sine alpha over 2 times sine 90 minus alpha over 2, which is great. Okay, and then we've got B would have to be the same thing, but with beta. So now, in terms of the angles, I can relate the radius to this whole side, which is great because I know the sides of my quadrilateral QRST that we're trying to work with. Okay. So if your tangent to 3 sides of a quadrilateral, and the middle of those 3 is side S, I can say that S is, we can factor out the radius from each of these and just say S is, that angle's alpha and that angle's beta. It's sine 90 minus alpha over 2 over sine alpha over 2 plus sine 90 minus beta over 2 sine beta over 2. Okay? Or if we know S, we can now rearrange and just say, all right, the radius of the circle that touches all 3 of these must be that s over these values, these ratios of sines. Okay? Now, because we're using right-angled triangles, we can actually go a little further with this work, and we can actually simplify things a little bit better. Okay? So let me point out what I'm talking about. We're working with things that look like sine 90 minus x. It's like minus alpha over 2 or beta over 2. But sine of 90 degrees minus x, that's the same as cosine of x. That's a nice little trig identity. So really, we're working with cos x over sine x, which is just cotangent. So really what we've got, the radius is going to be that middle side length of the 3 over the cotangent of half the angles inside my quadrilateral. Okay? So this is great. This gives me a perfect formula for my radii. So now we've got root 3, we have 3, we have 2. I know it actually should be a little more slanty than that. So let's say, there we go. So what we can do is we can say, all right, if I'm going to use these 3 sides, I'll have a radius of 2 over, what were these? 60, 60, 150, yeah, because it was a 30 up above and a 90. So if I use 2 as my middle side, we get 2 over cotangent, half of 150 is 75, and half of 60 would be 30. If we use, let's just go clockwise around this, root 3, it'll be root 3, the radius will be root 3 over cotangent 75, and then cotangent half of 90 was 45. And we use 3. Get a cotangent 30 there. And then coming all the way down to the bottom, the circle that you would make with 4 in the middle, you'll just have 2 cotangent 30s. Okay? Now, depending on how skilled we are, how familiar we are with trigonometry, you might actually know something like cotangent 30 or cotangent 45, but probably not cotangent 75. So I've already grabbed my calculator for this. Unfortunately, my calculator does not have a cotangent button, but that's okay. I can just do a tangent and then 1 over that. Because, of course, the inverse of the tangent is the cotangent. And so for the first one, I'm getting a 1. Okay? Just plain 1, which is kind of interesting. How about the square root of 3 divided by tan 75 inverse, or cotangent 75, plus the cotangent of 45. And there I'm getting 1.366, not a number I recognize, but if we go to the potential answers, now 1 is there. You would round up 13662 to 137. Okay? This would be answer A. This would be answer E. What about the other ones? Well, 3 divided by cotangent 45 plus cotangent 30. I'm getting the radius there would have to be 1.0980. So we'll round it up to 1.10 because it looks like their answers are to 2 decimal places. And then finally, 4 divided, I could combine the bottom here, make it 2 cotangent 30s. So really this is just 2 over cotangent 30. And I could speed things up slightly. So it's really just 2 times tangent of 30 degrees, which would be 1.1547. So I guess we'll round it down to 1.15. And if we look, so we definitely know D is out. But we've got the other answers are available. How do we tell which one's right? That's the trick now. Okay? So what we've got are sort of a series of possible radii. So if you just give me a side with a root 3, and you've got angles here, 150, and a right angle there, the biggest circle that you can draw that's tangent to these three sides is going to have a radius of 1.37. Right? That doesn't really take into account the 2 and the 3, and it definitely doesn't tell me where it sort of stops, and can the 4 go here? Can the 4 go here? Does the 4 have to go all the way out here, in which case there's enough room? So it's a little harder to work with that, because all you really used were the angles and the one side. These didn't come into it, and certainly the 4 didn't matter. And the 4 wasn't even a consideration. It's the side you're not using. So, well, what can we do? Well, if we look at it, we've got a few circles that are touching a few sides in common. Okay? So we got a circle with the 2 here, the root 3 here, 3 here, and a 4 here. So radius of 1 here. Now, at worst, that's our answer. At 1.00. Here it was a circle of radius 1.37. Can't remember what these ones were. One of them was 1.10, one of them was 1.15. So 3 was the 110, and this was the 115. Okay, now how do I tell which one's right? Well, only 2 of these circles touch these 2 sides. Okay, so what can we say? Well, imagine we've got our quadrilateral, and we do this same sort of idea of inflating a circle balloon in here. Now I'm going to inflate my circle balloon, but I'm going to make sure that it touches these 2 sides. And it can keep growing until it hits one of the other sides. Which side will it hit first? Well, it'll have to hit this side first, because that's the one with the smaller radius. As you inflate it, it goes from a small radius to a bigger radius. And as long as you just keep it touching these 2 sides, the circle balloon will move. But the first time it hits another one of the sides of my quadrilateral will be the 4 side. So you'll be stuck with this circle. So we definitely know this one's out. Okay. Now, what else can we do? Well, we can say, well, you might be able to do better than 1.0. We could do something like, you can't easily compare the 110 and the 1, but we could say something to the effect of, well, what about the 1.5? Well, you can compare it with this one, and so if you imagine inflating a circle balloon, but always making sure it touches those 2 sides, which third side of the quadrilateral is it going to hit first? The top, and that'll happen when the radius is 1. So yeah, you can draw a circle balloon that touches these 3 sides, but it's going to be too big. You will have already hit and then run through this other side. Okay. But we don't get this sort of conflict between these 2. Okay? So it looks like what you can do is you can inflate one that touches these 2 sides, and these 2 sides, and these 2 sides, and the first thing it'll do is touch the 4 down here with a radius of 110. And there's no harm with that. It's not going to hit this one, or it's not going to have previously hit one of the other sides. Okay? The only way a circle will hit this side first is if you're using 1.15, but that's a bigger radius. So it looks like 110 is our answer. Imagine these sort of circles blowing up and hitting 2 sides constantly. Which is the third side of the quadrilateral? Which of these 2 does it hit first? It hits this one when the radius is 110. It hits that one when the radius is 1.15. So that means I can draw a circle over here of radius 1.110 that does not hit this side at all. So we're good to go. This should be our answer. This is the biggest one that's left. 1.110 is the closest the largest radius can get to, and that's an answer of B. Okay, so it's interesting. Unfortunately, we didn't quite get a nice quick quadrilateral with an in circle, there wasn't a whole lot to work with here at the start, like not a whole lot of work that had to be done at the start. It was more jumping in to look at this in circle here. It didn't work, so we developed ourselves a formula for 3 sides, or rather a side and 2 angles, which I believe, just based on the answer, I think this might have something to do with the cotangent law. I seem to recall the cotangent law works if you know a distance between 2 things and angles, you can figure out how far away something is. I think that has something to do with the cotangent law and the Great Trigonometric Survey of India, but we'll leave that for, I don't know, a video of fun in the future, not a math contest video. But we had to develop this formula here, and then that gave us some possibilities, and we really just had to reason out which one was the best that we could use. This one wouldn't work, this one wouldn't work, this one does work without interfering with this one because you don't hit the 2 side. Okay, so that's the biggest one that's left standing, and that was B. Okay? So I'll get ourselves a fresh sheet of paper. We've got just one more question to go, and that's question 25. And we'll take a look at that in the following video. Take care, and of course, have yourself a wonderful day.